The objective of this lecture is to describe actions that can be applied to a rigid body, provide a description of Euler's laws for the motion of a rigid body, and to provide an example demonstrating the application of Euler's laws in rigid body mechanics. The first part of this lecture is going to be about actions applied to a rigid body. Now, the way this starts is as follows, is that a rigid body can both translate and rotate. So a rigid body can translate and rotate. The motion of a rigid body is different from that of a particle in that a particle can only translate. So that is, a particle cannot rotate. So, as a result, unlike a particle, unlike a particle, the actions applied to a rigid body must account for both translation and rotation. Now, what's important here is that for translation, the action applied to a rigid body is the same as the action that can be applied to a particle. Namely, the translational action applied to a rigid body is a force. Now, in the case of rotation, the action that results in pure rotation of the body is what's called a torque. Now, to deal with a torque, we actually have the following setup. Suppose we have a rigid body. Call this rigid body B. Suppose there's a point P on the body. We call a torque an action that causes only rotation of the body. So suppose that tau P is a torque applied about point P on rigid body B. Then tau P can be replaced equivalently with a so-called couple. Now, a couple actually works as follows, is that if we take this picture and we actually replace the torque with a couple, the couple has the following kind of effect on the body. Here's the body B again. Here's the point P. What we do is we take a distance away from the point P and we apply a force F and another force, negative F. So the pair of forces, F and negative F, you can see that the resultant is 0 because F plus negative F is 0. And what we do is we pick 2 points on the body. We're going to call these points A and B. And what we're going to do is we're going to call the vector that goes from P to A, we're going to call that vector rho. And then the vector from P to B is going to be negative rho. So basically the position of the position of A relative to P is going to be equal to rho, and the position of B relative to P is equal to negative rho, and then F is applied at A, so F is applied at A, and negative F is applied at B. Now, so the pair of forces F and negative F become a couple. Now let's suppose that we take another point on the body. I'm going to call that point Q. All right, so we know that the torque relative to P is equal to, well, it's equal to rho crossed with F plus negative rho crossed with negative F, which implies that the torque relative to P is equal to 2 rho crossed with F. So that's the couple that replaces the torque. Now suppose that we decide we're going to move to another point on the body Q. So let Q be another point on B. Then what we want to know is what is the torque relative to point Q due to the couple. So what we're going to do when we do this is we're going to see that the torque relative to point Q due to the couple is going to equal the position of A relative to Q crossed with F plus the position of B relative to Q crossed with negative F. But the position of A relative to Q is equal to the position of P relative to Q plus the position of A relative to P. And similarly, the position of B relative to Q is equal to the position of P relative to Q plus the position of B relative to P. So as a result, when thinking of this couple relative to point Q, we get the position of P relative to Q plus the position of A relative to P crossed with F plus the position of P relative to Q plus the position of B relative to P crossed with negative F. Now, let's suppose that we substitute. What do we get when we do the substitution? Well, we get the position of P relative to Q crossed with F, but the position of A relative to P is equal to rho, so we get plus rho crossed with F, plus the position of P relative to Q crossed with negative F, and then plus negative rho, which is the position of B relative to P, crossed with negative F, which is equal to, well, you can see here that the first and the third terms are opposite, so they cancel, and we get rho crossed with F plus another rho crossed with F, which is equal to 2 rho crossed with F, but that's equal to the torque relative to point P. So that implies that the torque relative to point Q is equal to the torque relative to point P. And because P and Q are arbitrary, the torque is independent of a particular point on the body. What that means is a pure torque applied to a rigid body B does not have a particular point of application, a point about which the torque is applied. But instead is applied to the entire body. That's really important. So torques have nothing to do with particular points of application. All right, so now we have two types of actions. So two actions applied to a rigid body. What are those two actions? The first one is a force, and the second one is a torque. Now, a torque, which torque causes only rotation, and then we have a force, and forces are applied in the same manner that they are applied to particles. But in the case of a force, now if we look at a rigid body, let's go back and draw this diagram. I have this rigid body B. Forces are applied at different points on the body. So if I have a bunch of points on the body, the force depends upon the point where it's applied to the body. So if I've got a force F1, another force F2, another force F3, and so on, all the way down F sub n, right? F sub n is applied to a particular point on the body. That's a system of forces. And then we could also have a resultant pure torque that's applied to the body. So from this, we have a force system. So the force system is going to be the set of forces. So the actions applied to a rigid body B consist of a system of n forces which are labeled F1 through Fn, and a resultant pure torque tau. So now let Q be an arbitrary point, then the moment due to the force system F1 through Fn together with the torque tau is defined as follows. We say that the moment relative to point Q is equal to the sum from I equals 1 to n of Ri minus Rq crossed with Fi plus tau, where Ri is the position at which, or I should say the position on B, is the position, I should say, associated with the point on B where the force F sub I is applied. So in other words, what that means is that if I have this rigid body B and there's a point on the body and the force is applied at that point, this location right here, this is the location on B where F sub I is applied. Then the moment due to all forces and the pure torque relative to an arbitrary point Q is defined as what I have above. Now we can use this information to be able to determine to be able to develop the laws of motion. So that's the next part of this, which is laws of motion. These are called Euler's laws of motion for a rigid body. So here's how this works. Is that Euler's first law is stated as follows. It says that the force applied to a rigid body is equal to the mass of the rigid body times the acceleration of the center of mass of the rigid body in an inertial reference frame. So n is an inertial reference frame, and a bar n is the acceleration of the center of mass in the inertial reference frame. Euler's second law, which accounts for rotation, so the first law accounts for translation, says that the moment relative to an inertially fixed point is equal to the rate of change in the inertial frame of the angular momentum relative to the inertially fixed point. O is a point fixed in the inertial reference frame n. Now, those are the two laws, but it turns out that it's not always convenient to use an inertially fixed point. So it is not always convenient to apply Euler's second law relative to an inertially fixed point. So what are the options? So there are two options. Are two alternatives to an inertially fixed point. 1, which is the center of mass of the rigid body, and 2 is an arbitrary point. So let's start with the center of mass, okay? So Euler's law, or Euler's second law, using the center of mass as the reference. Now in this particular case, what we're going to do is we're going to start with the definition of the angular momentum. So we know that the angular momentum relative to an inertially fixed point is equal to the angular momentum relative to the center of mass plus Rho minus R bar crossed with M times VO in N minus V bar in N. So what we're going to do is we're going to take the rate of change. So we know that the rate of change in the inertial frame of the angular momentum relative to O in the inertial frame is equal to the rate of change in the inertial frame of H bar N plus the rate of change of the second term. So we can write this out if you want to. d dt in N of Rho minus R bar crossed with M times VO in N minus V bar in N, right? But this is equal to the rate of change in N of H bar in N plus, now if I take the rate of change, I've got a product. So the first term in the product gives me VO minus V bar crossed with M times VO minus V bar, but that's equal to 0. The second term gives me RO minus R bar crossed with M times the acceleration of O minus the acceleration of the center of mass, right? But O is an inertially fixed point, right? So, but O is fixed in N because O is inertially fixed. So that implies that the acceleration of O in N is equal to 0. So therefore, we obtain that the rate of change in N of HON is equal to the rate of change in N of H bar N plus RO minus R bar crossed with minus MA bar in N. That's what's left. But from Euler's first law, we have that MA bar in N is equal to F. So therefore, the rate of change in N of HO in N is equal to the rate of change in N of H bar in N plus, or say minus, RO minus R bar crossed with F, which is the resultant force acting on the body. But from Euler's second law, what do we have? We have that the rate of change of the angular momentum relative to point O in the inertial frame is equal to the moment relative to point O. So that implies that the moment relative to point O, if I do the substitution, is equal to the rate of change in N of H bar in N. Write that N a little bit more clearly. Minus RO minus R bar crossed with F. But the moment relative to point O, from the definition that I have here, if I go back, the moment relative to point O is equal to the sum from I equals 1 to N of Ri minus Ro crossed with Fi plus tau, and also the force is equal to the sum from I equals 1 to N of fi. So if I substitute those up above, what do we get? So then the sum from I equals 1 to n of Ri minus Ro crossed with Fi plus tau is equal to the rate of change in n of h bar in n, and then you get minus Ro minus R bar crossed with the sum from I equals 1 to n of Fi. So now let's rearrange this. So this gives the sum from I equals 1 to n of Ri minus Ro crossed with Fi, and then I can add over this. I get plus, and I can bring this whole thing to the inside. So I get the sum from I equals 1 to n of Ro minus R bar crossed with Fi. I just brought that last term over to the other side. Plus tau is equal to the rate of change in n of h bar in n. Now let's look what happens when we actually simplify this last expression. So what do we get? We get the sum from I equals 1 to n. Now look what we have here. We have Ri minus Ro and then plus Ro minus R bar all crossed with Fi. So this gives Ri minus R bar crossed with Fi plus tau is equal to the rate of change in n of h bar in n. And that says that, but you see this last term here, this is equal to the moment relative to the center of mass. So this says the moment relative to the center of mass is equal to the rate of change in n of h bar n. So that's the alternate form of Euler's law. So this is Euler's second law. Relative to center of mass of the rigid body B. And you can see that it looks very similar to what the original statement is. The original statement is that the moment relative to an inertially fixed point is equal to the rate of change of the angular momentum relative to an inertially fixed point. So that's what you get for the center of mass. The next is, so just like we did this over here, we said Euler's second law using the center of mass as the reference. Now we're going to say, we're going to do Euler's second law using an arbitrary reference point. Now, what do we get in this particular case? Well, when we use an arbitrary reference point, we know that the angular momentum relative to an arbitrary point is equal to the angular momentum relative to the center of mass plus RQ minus R bar crossed with M times VQ in N minus V bar in N, where Q is an arbitrary point. So again, let's take the rate of change. So therefore, the rate of change in n of HQ in n is equal to the rate of change in n of H bar in n. And then we get plus, now we got the rate of change in n of RQ minus R bar crossed with M times VQ minus V bar in n. Now, let's go through this calculation. This is equal to the rate of change in n of H bar in n. And then we got plus, now we got a product rule again. The first term in the product rule is the same as we get the rate of change of RQ minus R bar, which gives VQ minus V bar, crossed with m times vq minus v bar, so that disappears. So we just get rq minus r bar crossed with m times the acceleration of q in n minus the acceleration of the center of mass. But in this case, q is arbitrary, so that acceleration of point q is not 0. So what we're going to do now is we're going to simplify this result. So therefore, the rate of change in n of hq in n is equal to the rate of change in n of h bar in n. And then, when we simplify here, we get rq minus r bar crossed withmaq, and then we get another term. We get plus, or I should say minus, rq minus r bar crossed with ma bar in n, and that comes from the second term here. Now again, we note that from Euler's first law, we have that F equals ma bar n, and also from the center of mass result, we have that the moment relative to the center of mass is equal to the rate of change in the inertial frame of h bar in the inertial frame. So therefore, if we substitute both those results into this, we get the rate of change in n of hq in n is equal to m bar, and then we get plus rq minus r bar crossed with maq, and then we have minus rq minus r bar crossed with f. But now again, we can substitute, and we can recall that m bar is equal to the sum from I equals 1 to n of ri minus r bar crossed with fi, and also that f is equal to the sum from I equals 1 to n of fi. So given that we have those two relationships, we get the following. We have that the rate of change in n of hq in n is equal to, actually we have to write one thing here, plus tau. Sorry, there's a torque there. So here we get the sum from I equals 1 to n of ri minus r bar crossed with fi plus tau. That's this term. And then we get, now I'm going to flip the sign here. I get minus r bar minus rq crossed with maq in n. And then we have this last term here, which is minus rq minus r bar crossed with the sum I equals 1 to n of fi. So then this gives that the rate of change in n of hq in n is equal to, well, now look what we've got here. We've got the sum from I equals 1 to n. We've got ri minus r bar, and then we have plus r bar minus rq crossed with fi. When I take the rq minus r bar inside the summation of the last term, and then I have plus tau, and then I have minus r bar minus rq crossed with maq in n. So therefore, we get the result that the rate of change in n of hq in n is equal to the sum from I equals 1 to n of ri. I've got minus r bar plus r bar, so I get ri minus rq crossed with fi plus tau, and then I've got minus r bar minus rq crossed with maq q in n. But now look at this term right here. This term is equal to the moment relative to point q. So we then obtain that the rate of change in n of hq in n is equal to the moment due to all forces and pure torques relative to point q minus r bar minus rq crossed with MAQ in n. So let's summarize all this of Euler's laws. Okay? The first is this, that Euler's first law only pertains to the center of mass. It has nothing to do with anything, any point other than the center of mass. It says that F is equal to the mass times the acceleration of the center of mass in the inertial frame. Euler's second law has three different forms. What are those three forms? The first form is that for an inertially fixed point, the moment is equal to the rate of change of the angular momentum relative to the moment relative to the inertially fixed point, where O is fixed in the inertial frame n. The second form is for the center of mass, the rate of change of the angular momentum relative to the center of mass is equal to the moment relative to the center of mass. This is for center of mass. And then the third one is that the rate of change in n of the angular momentum relative to an arbitrary point is equal to the moment relative to the arbitrary point minus r bar minus rq crossed with MAQ in n, and this is for q is an arbitrary point. Okay, now I want to focus on one thing here, that this form right here is the one, this is the preferred form. So when you're doing problems in rigid body mechanics, the one that you want to use most often is the one where you're dealing with the center of mass. It's the easiest one. Y is the center of mass. So Y generally use the center of mass as the reference. Why would we do that? Well, recall that the angular momentum relative to the center of mass is equal to the moment of inertia of the body multiplied by the angular velocity of the body in the inertial frame. This is the fundamental angular momentum for a rigid body. So unless you've got a reason to move to another point, you don't want to use anything else. So it's useful to always write things in terms of this, because that is the constituent equation. So as a result, it is preferable to use the center of mass of a rigid body as the reference point, because h bar is required for any rigid body dynamics problem. So in other words, no matter what the problem is, you're always going to have to compute the angular momentum relative to the center of mass. And also, it is required to compute the acceleration relative to the center of mass. So as a result, you have two quantities. So therefore, the center of mass is the conceptually most straightforward reference point to use. So unless you have a good reason, you don't want to use anything other than the center of mass as the reference point. So now let's actually see how all of this plays out in an example. So let's do the following problem. And this will be a starting point for us to do other problems in the future, but it's a good first problem. So what we're going to do in this problem is we have a uniform slender arm, and it is suspended from an inertially fixed hinge point O. The angle formed by the vertically downward direction and the arm is theta. The center of mass of the arm, because it's uniformly distributed, is at C. The mass of the arm is M, the length of the arm is L, and there's gravity acting downward. Now, what we're going to do is the objective of this problem: determine the differential equation of motion in terms of the angle theta. Now, remember that we had said earlier that we were always going to use a principal axis coordinate system in order to be able to develop the moment of inertia tensor and resultant angular momentum. So in this particular problem, we're going to use two coordinate systems. The first coordinate system is going to be fixed in the inertial frame. It's going to have its origin at point O, and the basis is going to be fixed in the ground or the inertial frame. So the origin, so this is fixed in the ground, which is the inertial frame, with origin at O. Now I'm going to have a second coordinate system. The second coordinate system is going to be a coordinate system defined by three vectors: ER, E theta, and again EZ. And ER is going to be along OC. EZ is out of the page, which is the same as what I had before. Now this is going to be fixed in the arm with origin at point C, which is the center of mass. And it turns out now that this coordinate system, I'm going to define this coordinate system, is as C together with the basis ER, E theta, EZ is a principal axis coordinate system for a slender uniform arm or rod. All right, so we're going to call this basis, we're going to give it a name because we're going to be using it over and over again. We're going to call it E. And we're going to just keep referring to it the entire problem as E. Now what we're going to do is we're going to develop all the equations using Euler's laws. So let's go back. So we need the acceleration of the center of mass and the angular momentum relative to the center of mass. Okay, so How do we get the acceleration of the center of mass? So the first thing we need is we need the position of the center of mass. That's equal to L over 2 ER. So now, given that we're working with that basis, we know that the angular velocity of the arm relative to the ground is equal to theta dot Ez. Now notice that this position of the center of mass is also equal to the position of C relative to O. So that's for completeness. Because where are we measuring from? We're measuring from an inertially fixed point. All distances have to be measured from an inertially fixed point. So then the velocity of the center of mass is equal to the rate of change of the position of the center of mass in the ground, but that's equal to the rate of change of the position of the center of mass relative to the arm plus the angular velocity of the arm in the ground crossed with the position of the center of mass. And you'll see here that the first term is 0, and so that gives that the velocity of the center of mass is equal to theta dot Ez crossed with L over 2 ER, which is equal to L theta dot over 2 E theta. Next, the acceleration of the center of mass in the ground is equal to the rate of change in the ground of the velocity of the center of mass as viewed by an observer fixed to the ground. That's equal to, again by the transport theorem, the rate of change of the arm of the velocity of the center of mass in the ground plus the angular velocity of the arm in the ground crossed with the velocity of the center of mass as viewed by an observer fixed to the ground, which is equal to, well, if we take the rate of change, we get L theta double dot over 2 E theta plus theta dot Ez crossed with L theta dot over 2 ER. So therefore, the acceleration of the center of mass, if I put these back in the order of the basis vectors, Ez crossed with ER, Ez crossed with E theta, my apologies, Ez crossed with E theta is equal to minus ER. So we get minus L theta dot squared over 2 ER plus L theta double dot over 2 E sub theta. So that's the acceleration of the center of mass. So next, the angular momentum relative to the center of mass is equal to the inertia tensor relative to the center of mass of the arm multiplied by the angular velocity of the arm in the ground. But the inertia tensor relative to the arm, when it's expressed in this basis E, can be written in matrix form by the following diagonal matrix. Now, for a uniform slender arm, we can actually look this up in a book. We have the following, that IR bar is equal to 0 and I theta bar is equal to IZ bar, which is equal to ML squared over 12. That just comes from looking things up in a book. So also, we know that the angular velocity of the arm as viewed by an observer fixed to the ground when expressed in this coordinate system defined by this principal axis basis E is equal to 0, 0, theta dot. So as a result, the angular momentum relative to the center of mass when expressed in this basis E is equal to the inertia tensor expressed in the basis E multiplied by the angular velocity of the arm in the ground expressed in this basis E, which is equal to, so we get 0 for that first one, ml squared over 12, and then ml squared over 12, and that's multiplied by 0, 0, theta dot, which is equal to, when we're all done, we get 0, 0, ml squared over 12 theta dot. So that's our final result. As a result of that, we can actually put this back in vector form because the only component that survives is the z component, and we get ml squared over 12 theta dot ez. So now look what we have. So we have, let's see what we have so far. So we now have that the acceleration of the center of mass is equal to minus L theta dot squared over 2 ER plus L theta double dot over 2 E sub theta. And we have the angular momentum relative to the center of mass is equal to ml squared over 12 theta dot Ez. So now we can start applying the laws of kinetics. So in order to do that, we need to draw the free body diagram. So here is the arm. What are the forces that are, and possibly pure torques, there aren't any pure torques in this case, acting on this body? Well, in order to make this a little bit easier, let's move this down a little bit, just so that we have a little bit more room to be able to work with. So there's the arm. So we have gravity, which acts at the center of mass, and then we have some reaction force. I'm going to put this off in some arbitrary direction. Let's actually make it really clear that it's off in some arbitrary direction, which is r. Now, r does not lie along the arm. This is very important. R does not lie along the direction of the arm, because this is a rigid body. It's a distributed mass rigid body. It's not a particle. So as a result, R has two components, R sub r ER plus R sub theta E sub theta. And also, the force of gravity is equal to mg times Ex, because Ex is in the downward direction. So now, we're going to do this using two different methods. The first one is going to be using the center of mass as the reference, and then just to show you how this works when we actually, because I said the center of mass is the preferred way to do this. We're also going to do this using the hinge point as the reference. So method one is center of mass as the reference. Now, this is not always the algebraically easiest way to do things, but it is the most straightforward way conceptually. So we're going to apply Euler's first law, and we're going to apply the moment balance relative to the center of mass. So the form of Euler's second law relative to the center of mass. So here we got Euler's first law. And here we have Euler's second law. Now let's go through and let's do this. We already have the acceleration and we have the angular momentum. So first, let's just get the rate of change. The rate of change in the ground of the angular momentum relative to the ground. And actually, you know what? We can go back over here, and we should have done it this way to begin with, but we'll do it now. Which is that this is the angular momentum relative to the center of mass in the ground, and this is the ground. Okay, so this is equal to ml squared over 12 times theta double dot Ez, and that's because Ez is fixed in the ground, which is the inertial frame. So now we've computed the rate of change of the angular momentum. So the next thing we need to do is we need to compute the force. So the force is equal to the reaction force plus the force of gravity, which is equal to r sub r er plus r sub theta e theta, and then plus mg ex. And that has to equal the mass times the acceleration of the center of mass, which is equal to m times minus L theta dot squared over 2 ER plus L theta double dot over 2 E sub theta. So therefore, we obtain that R sub R ER plus R sub theta E theta plus mg EX is equal to minus ML theta dot squared over 2 ER plus ML theta double dot over 2 E sub theta. Now, we know that from the diagram that EX is equal to, well actually let's just look at it, let's draw it over here. Here's EX, there's ER, and there's E theta, right? So as a result, this angle is theta. So EX is equal to cosine theta ER minus the sine of theta times E theta, because that direction is negative E sub theta. So as a result, we get R sub R ER plus R sub theta E theta, and then we've got plus mg cosine theta ER minus mg times the sine of theta times E theta is equal to minus ml theta dot squared over 2 ER plus ml theta double dot over 2 E sub theta. So now we can break this up into components. So the first equation that we get is we get R sub R, this is the ER component, we get R sub R, and then we've got plus mg cosine theta is equal to minus ml theta dot squared over 2. The second equation we get is we get R sub theta minus mg times the sine of theta is equal to ml theta double dot all divided by 2. Notice that there are unknown reaction forces in this. So now we're going to apply Euler's second law. So next, we need to compute the moment relative to the center of mass. Well, the moment relative to the center of mass, if you go back to the free body diagram, you can see that gravity goes through the center of mass. So what we're left with is RO minus R bar, because the force O acts at the force R acts at point O. So we get RO minus R bar crossed with R. But RO minus R bar is equal to minus L over 2 ER crossed with R sub R ER plus R sub theta E sub theta. So this gives that the moment relative to the center of mass is equal to minus L R sub theta all divided by 2 EZ. ER crossed with ER is 0, ER crossed with E theta is EZ. And that has to equal the rate of change in the ground of the angular momentum relative to the ground, which we already computed to be ml squared over 12 theta double dot EZ. So as a result, we wind up with a third equation. So the third equation says that minus L R sub theta all divided by 2 is equal to ml squared over 12 theta double dot. Now we can use 1, 2, and 3 to obtain the differential equations. To obtain the differential equation. So how are we going to do that? So the first thing is that we're going to solve 3 for R sub theta. What do we get when we do that? We get R sub theta is equal to minus ml over 6 theta double dot. All I did was just, multiply both sides by 2, divide by L. And then now we're going to substitute R sub theta into 2. We don't even really need 1 for this whole thing. We just need 2. So what do we get? We got R sub theta, which is equal to minus ml over 6 theta double dot. And then we have minus mg sine theta. And that has to equal ml theta double dot over 2. So ml over 2 theta double dot. So if we put everything on one side of the equation, we've got ml over 2, ml over 6. ml over 2 is equal to 3 ml over 6. So we've got 3 ml over 6 plus ml over 6, which is 4 ml over 6, which gives 2/3 ml theta double dot. And then if I bring the mg sine theta over to one side, I get that. That is the differential equation. Now, what I'm going to do here in order to make this look like what we might get when we finish this is with using the other method is just for completeness. I'm going to put this on the side. If we multiply by L, we get 2/3 ml squared theta double dot plus mgl times the sine of theta is equal to 0. That's multiplying by L. I'm just going to keep that multiplying by L. I'm only going to do that just because when we do the second method, which is going to use the hinge point, we're going to get a slightly different result. So we'll see how this works. So method 2 is hinge point as the reference. Now it turns out that this method is actually simpler than the first one, but again, I say that unless you really know how to do it, you don't want to use anything other than the center of mass. So O is an inertially fixed point. So therefore, the moment relative to point O is equal to the rate of change in the ground of the angular momentum relative to point O. So in order to do this, we need the angular momentum relative to point O. Well, the angular momentum relative to point O is equal to the angular momentum relative to the center of mass plus RO minus R bar crossed with M times VO minus V bar. But we already have the angular momentum relative to the center of mass. It's equal to ml squared over 12 theta dot EZ. Now, for these other terms, RO minus R bar is equal to minus L over 2 ER, and then it's crossed with M. Now, the velocity of O is 0, and the velocity of the center of mass we already derived to be L theta dot over 2 E theta. So this equals ml squared over 12 theta dot EZ, and then we've got ER crossed with E theta is EZ, so we get plus ml squared over 4 theta dot EZ. Okay, so that equals ml squared over 3 theta dot EZ. Now, as a result, we get that the rate of change in the ground of the angular momentum relative to point O is equal to ml squared over 3 theta double dot EZ. So now, as a result of that, we now can compute the moment relative to point O. The moment relative to point O. What's the moment relative to point O? Well, we have to go back to the free body diagram. If we go all the way back to the free body diagram, notice that the only thing that creates a moment relative to point O is gravity. So as a result, we've got R bar minus RO crossed with mg because gravity acts at the center of mass. So that's equal to L over 2 ER crossed with mg. Now, what's our expression for mg? Let's go back and get mg. mg is equal to mg ex, but ex is equal to cosine theta er minus sine theta e theta. So this gives mg cosine theta er minus the sine of theta times e theta, which is equal to mgl over 2, and then er crossed with er is 0, er crossed with e theta is ez, so this gives me minus mgl over 2 sine theta ez. Then mo is equal to the rate of change in the inertial frame of the angular momentum from Euler's second law, which says that minus mgl over 2 times the sine of theta times ez has to equal ml squared over 3 theta double dot ez, which gives ml squared over 3 theta double dot is equal to minus mgl over 2 sine theta, which can be rearranged to give ml squared over 2 ml squared over 3 theta double dot plus mgl times the sine of theta is equal to 0. And you can see that that's the same result we got here. That's why I multiplied that last equation by L, just to be able to see that. So this example actually demonstrates the ability to use two different forms of Euler's second law. The first one being relative to the center of mass, the second one being relative to an inertially fixed point. Now you can see that the approaches have differences because of the points. But the key difference is, see, we have to compute the angular momentum relative to the center of mass no matter what. So even though the first approach, which was to use the center of mass, is a little bit extra, has a little bit extra algebra in it, it's conceptually a little bit more straightforward because you have to do any auxiliary calculations. You just apply Euler's first law, Euler's second law, and you just go through the algebra after you're done. When you do this with an inertially fixed point, you notice that if you go back here, you'll see I had to transfer the angular momentum. If you look right here, I had to transfer the angular momentum from the center of mass to point O. And this is the step that gets a little bit hard to deal with, because if you don't always know what to do there, you may make a mistake there without realizing that you've made the mistake, and so that creates a bit of a problem. So when in doubt, it's better to actually do this with the straightforward form using the center of mass. So that takes us to the end of this particular lecture. In the next lecture, we're going to study more examples which show how to apply Euler's laws to rigid body mechanics.